In this video, we're going to talk about impulse and how impulse relates to momentum and how we can kind of understand how impulse applies to everyday life. And I guess before we get into the actual impulse, we want to go back to momentum. Remember that momentum, P, was equal to mass times velocity. And we're going to go with another three variable formula that we've also had and kind of relate that to momentum too, which was Newton's second law, F equals ma. Now, we're going to start with the A, the acceleration, because acceleration was really equal to the change in velocity over the change in time. So we kind of re-add the rest of this yet. We end up with m delta v over delta t is equal to f. Well, if I go up to here, if I kind of expand this a little bit, if I want to know about the change in momentum, that's going to be the mass times the change in velocity. And if we kind of look, we're seeing this show up here. So what we're saying is, well, okay, force is the change in momentum over the change in time. And then, okay, well, let's get this change in momentum by itself. So we're going to multiply both sides by the change in time. And that brings us to what impulse is kind of thought about as. F delta t is equal to delta p. So we derived a kind of a simple formula here, but the idea is when I apply a force to something for any time, its momentum is going to change. And that's what impulse kind of is. So if I give a real basic definition of impulse, and it's going to be a little ugly here, it's how a force applied to an object for a certain time, certain with n, causes the momentum to change. Force applied for a time, change in momentum. So the idea is whenever I have a force applying to an object, momentum should change. The longer I apply the force, the more the momentum will change. And that's probably pretty simple when you kind of think back to here. The longer something's accelerated, the longer the force needs to be applied to that. So there's a couple different ways we can kind of look at this. We're going to really concentrate on this force-time relationship here. And we're going to take something very simple. We're just going to talk about someone jumping from 1 meter. Kind of say, okay, we have a 1 meter box. And here's the ground that they're jumping down to. Here's our stick person. When they jump from this location down to here, this guy's just going to keep his legs straight. When we jump the other direction, just to kind of give us two different sides to work with here, I'm going to redraw the person. This person here is going to jump, but they're going to bend their knees. And the question is, how are these different? And I'm sure many of you have done something like that, where you just jump from maybe a couple stairs down. And what you probably notice is this has a little bit of pain. Not a lot, but just a little more painful than what this is. And the reason is because of this right here. Bending your knees increases the time. By increasing the time, the momentum for this person jumping to here and this person going to there is the same. Change of momentum is the same for both. So the idea then is if our change of momentum is the same, jumping from 1 meter down to the bottom, then if we're increasing time, we're going to have to decrease the force. Or another way to kind of show you this is kind of just making these things bigger. I have a small force, but I have a large time. Here I have a large force, but a little time. I kind of made the force bigger because this is more painful. This happens in a faster amount of time, or it takes less time for that to happen. When you bend your knees, it takes longer for that to happen. So it takes less force, which means you feel less pain in your joints. So those are some simple examples of impulse and how it applies to everyday life. We're going to look at some other visual examples. Here we have some shock absorbers on a bicycle right here. What does that do? Shock absorbers essentially make this collision last longer. So again, here we're going to have less force because we have a greater time interval. And honestly, all of these examples are kind of going to center on the same idea. The wheel will be in contact with the ground longer as you're going over a bump, which means you're going to feel less of a force pushing up through the bike. So the bike ride doesn't seem as bumpy. Airbags are really a very simple idea where if we can make this collision last longer, a longer lasting collision means less force on the driver and the passengers, and that might be the difference between surviving a crash and not surviving a crash at high speeds, obviously. And this, you can also see the side airbags are also deployed in case they have a side collision. So sometimes it might be a factor of a hundredth of a second, but that hundredth of a second that the collision is increased, the collision time gets increased, might reduce your forces that you feel by a factor of 10 or more. So if there's 10,000 newtons of force coming on this driver, which is a pretty substantial amount of force, they really only experience 1,000 newtons of force. And finally, we have a trampoline here. You can see someone that's going to fall horizontally on their trampoline. These little kids here aren't even worried about this. They know this person is going to hit here, bounce straight back, and no big deal. Again, the longer you're in contact with the trampoline, the less force you feel, and it's not going to hurt you as much. Where if you did this on the ground, it would be very, very painful because you'd hit and the collision would take very little time. So that's kind of our main idea that we're using right now with impulse. This could be switched also with athletics. A lot of times you hear athletes are told to follow through. So if you're hitting a baseball, by trying to make the bat in contact with the ball as long as possible, by following through, now you're having this force push on the baseball longer, so the ball will go farther. And the same idea with golf and tennis and really any sport where you're hitting a ball with some type of racket or bat or stick. To kind of give us another visual with this, a watermelon. If we drop a watermelon from 10 feet, that's about the height of a basketball hoop. We know that after dropping a watermelon 10 feet, it's probably not, the chances of a watermelon surviving a 10-foot drop aren't good. And you expect this to kind of be splattered. Here's my broken up watermelon picture. But if we drop it in the water, it's able to make it and survive because, again, when you're looking at the time it takes to go from the surface all the way down to the bottom, is just simply going to take more time. The bottom where it stops, not necessarily the bottom of the pool. It's going to take more time than what this did, which creates, or requires, I should say, less force. Because the change of momentum, the change delta P, is the same for both. They're both going to have some speed created by this 10-foot drop, and they're both going to end up with a final speed equal to 0. So if you can increase the time, you can decrease the force so it's not going to be destructive to a watermelon. Or if an airbag, it's not going to be very dangerous to you. So again, changing time to decrease force. Okay. One final example that we're going to look at with this is when you're doing labs, you might have a force versus time graph. Or a lot of times IB will ask questions about if a force is applied to a certain object for a certain time, what is the speed? In this case, we're talking about a golf ball being hit by a golf club. And a lot of times these problems can be a little challenging because you really can't get information off a curve like you can a line graph. But there's one thing you have to remember is that we can find the area of this. And if I found the area, it would have units of newtons times seconds. Well, is that a useful unit? Not necessarily, it's obvious, but we have to take a newton and break it down. Newton is a kilogram times meter per second squared. We're going to multiply that by a second. So what happens basically is this squared term goes away. And we end up with just kilograms times meters per second. Well, that's momentum. And that kind of tells us is, okay, this momentum is changing somehow. So if I can find the area underneath this curve here, that will tell me how my momentum changes. If I can find my change in momentum, the change in momentum is going to equal mass delta V, that would help me find my change in velocity. This one started from rest, so I would just add whatever this change in velocity is to 0, and that would be my new velocity. So we got to kind of take a more simplified approach. We can't just jump in here and find the area of this. We have to use approximate areas. So, this is kind of like a triangular shape. If you kind of go up to here and think about that, it's not a perfect triangle. And then in the middle, oops, sorry about that. I'm going to bring that back up. Let me move these out of here and try to clean this up a little bit. If I put some shapes in here, and we kind of look, okay, here's my middle area. This takes up most of it. There's a little bit of extra up here, but we're just going to approximate this. This triangle tool might not work the same, but let me just try it once. If I move this over here, it's not bad. Let me move that up into place here. You can kind of see that this triangle is a decent way to approximate what's going on with this side over here. And because these are both identical, we can assume that this triangle and this triangle are the same. Some of it's not quite being accounted for, but we have a little extra area down here at the bottom. Oops, sorry. There's our person from the trampoline from before. If I copy and paste this, and if I can flip this horizontally, yep, I left to right. Okay, so if I kind of put this in here, now you can see here are our areas that we are going to approximate. So it's a little cleaner than what we did before. So what are we going to do? We're going to approximate area 1, area 2, and area 3. Okay, area 1's a triangle, so area 1 is equal to 1/2 base times height. Oops. Base times height, what we want here. 1/2. Now my base is this time, 0.02 to 0.03, which will be 0.01 seconds, times the height, which will be 200 newtons. So when I multiply this out, it comes out to 1 newton seconds. Area 3 is the same, because these triangles are the same, just flip. Area 2 is just simply a rectangle, which would be base times height. The base is going to be the same, 0.01 seconds. But the height this time is 200 newtons, so it's very similar. But this one turns out to be 2 newton seconds. Our total area is equal to 4 newton seconds. Again, not really totally useful, but we got to go back to this idea. Change in momentum is change in velocity times the mass. So if I want to find the change in velocity, I'm going to take the change in momentum divided by the mass. Oops, mass, not. Change in velocity equals change in momentum. So we have 4 newton seconds for our change momentum, divided by our mass, which is in grams here, which is going to be 0.0459 kilograms. Remember, always have the appropriate units. And that's going to give us a final change in velocity of 88.8 meters per second, which is 180 plus miles per hour. This is probably what we're used to using. Miles per hour is probably what you're used to using here in America, but 88.8 meters per second is what we're going to be required to use in IB and other SI measurements. So that concludes our impulse video.